Big Bang happened 13.8 billion years ago. All matter, all energy, and even space itself were compressed into an extremely hot and dense state. Now here's the question. If the universe is 13.8 billion years old, and nothing can travel faster than light, then nothing should be farther than 13.8 billion light years away from us. But when we observe the universe today, we see galaxies that are over 30, 40, even 46 billion light years away. If light is the fastest thing in existence, then how did the universe become so large in such a short time? This sounds like a paradox. The universe itself has been expanding, and not just expanding faster than light in its early moments. Now wait, doesn't science say that nothing can travel faster than light? Yes, nothing can move through space faster than light. But space itself can expand at any speed. When the Big Bang occurred, it was not an explosion in space, it was an expansion of space. But here's something even more surprising. Instead of gravity slowing this expansion down, the expansion rate increased. Why? Why didn't gravity pull everything back together? The expansion rate of the universe is called the Hubble constant. It tells us how fast galaxies move away from each other per unit distance. But how do we calculate it? There are two major methods. The first method uses something called the cosmic distance ladder. Scientists observe very bright objects like supernovae. If we know how bright something actually is, and we measure how bright it appears from Earth, we can calculate its distance. Then we measure how much its light has shifted toward red wavelengths, a phenomenon called redshift. The more redshift, the faster it is moving away. Using this method gives one value for the expansion rate. The second method looks at the cosmic microwave background, leftover radiation from about 380,000 years after the Big Bang. This radiation acts like a baby picture of the universe. By studying tiny temperature fluctuations in this radiation, scientists can calculate how matter was distributed in the early universe and predict today's expansion rate. But here's the problem. These two methods give slightly different answers. One says around 67 kilometers per second per megaparsec. The other says around 73 kilometers per second per megaparsec. Both are close, but not identical. And this difference has confused cosmologists for years. Then came an important breakthrough. When two neutron stars collided in a distant galaxy, they produced both gravitational waves and light. For the first time, scientists could measure distance using gravitational waves and velocity using light from the same event. This gave a more independent estimate of the universe's expansion rate, and it supported the idea that the universe is indeed expanding and possibly accelerating. Now here comes the deeper question. If the universe began in a hot, dense state, how did it grow so enormously large? The answer lies in a concept called inflation. In the tiniest fraction of a second after the Big Bang, the universe expanded exponentially. Imagine baking a loaf of bread with raisins inside. As the dough rises, the raisins move apart, but the raisins are not moving through the dough. The dough itself is expanding. Similarly, galaxies are not flying through space away from each other. Space itself is stretching. And during inflation, space stretched incredibly fast. That's why we can see regions today that are far beyond what simple light travel time would suggest. But something even stranger is happening. The expansion is not slowing down. It is accelerating. Gravity should pull matter together. So why is the universe speeding up? The leading explanation is something called dark energy. Dark energy behaves like a kind of anti-gravity. It creates a pressure that pushes space outward. And here's the shocking part. Everything we can see, stars, planets, galaxies, makes up only about 5% of the universe. About 27% is dark matter, and nearly 68% is dark energy. Which means the universe is mostly made of things we do not fully understand. And if this acceleration continues, many distant galaxies will eventually move so far away that their light will never reach us again. In the far future, observers in our galaxy might see only the Milky Way and nearby galaxies. So when we ask about the beginning of the universe, we are not just asking how it started. We are asking how it became so large, how it continues to expand, and what invisible forces are shaping its destiny. The Big Bang explains the early, hot, dense state. Inflation explains the rapid early growth. Dark energy explains the current acceleration. But the ultimate question remains: why did the Big Bang happen at all? What triggered inflation? Why do the laws of physics exist? The beginning of the universe is not just a story of an explosion. It is a story of space stretching, of gravity competing with expansion, of mysteries that still challenge our understanding. And the more we discover, the deeper the mystery becomes.